All right, what is the field of fractions of a field? Well, what does your intuition tell you? The point of creating, the point of our discussion of fields of fractions is to take something that's not quite a field and make it a field. So if you already have a field, then making its field of fractions shouldn't do anything because you've already got what you're looking for. So we want to prove that. So let f be a field and f prime its field of fractions. I claim f equals f prime. Okay, so recall, what do we know about f prime? F prime equals a over b, where a, b, and f, and b is not 0. Then here, we know by definition a over b equals c over d, if and only if AD equals BC. But because this is a field, we can, and because B and D are invertible, are non-zero, we can invert them, and this is AB inverse equals, let's see here, CD inverse. So turns out f prime equals AB inverse, AB and F, B is not equal to 0. Yeah, and this was I'm not sure if this is fully rigorous, but we even discussed this in the in fact, what we started with was we actually started with this definition of a field of fractions and actually wrote this relation by writing AB inverse equals A over B. So I think I could have done this a little nicer, but whatever. I don't want to spend too much time on this because it should be kind of obvious that like at first I was I thought about it for a little bit and then I'm like, oh duh, it should be itself. So, and it turns out this is just a completely trivial proof, so I don't want to spend too much time on it. Even though I'm babbling about how much time I don't want to spend on it, which is taking time. Anyways, so your f prime is this. Then clearly f equals f prime. Now this one direction, it's clear that f is a subset of f prime because you just take b to be equal to 1, and then f prime is literally all the elements of f, all the elements of f can be written as the element times 1 inverse. So you just letting b equal 1 here, then you get f. And then for the other direction, you take an element a b inverse, then b is non-zero, so b inverse is in f because it's a field, and then a is in f, and so you multiply the two things, you get something that's in f, and so f prime is a subset of f. F prime is the subset of f, and so f equals f prime. So they're equal as sets. 1 is just 1 over 1, and 0 is 0 over 1. This is, again, just associating elements in your original domain with the elements in the field of fractions. This is how we did it before. This is how we do it now. Multiplication is identical since, and of course this whole thing, this is really not necessary, but I'll write it out anyways. This is all working in f prime here, but now when we convert to f, we have AC B inverse D inverse because all the things that are in the denominator become inverses. So this is AB inverse CD inverse, which is of course what the multiplication would be as elements of f, and pluses since. So this shows you how multiplication in f prime is the same as multiplication in f, and then going the reverse is easy because if you want to multiply two things in f, then you just put them over 1 and it becomes the same. Pluses, since a over b plus c over d equals ad plus bc over bd. And what's that? That's ADB inverse D inverse plus BC B inverse D inverse. Fields are nice, and you can commutativate. And so you get that, and then you get f equals f prime. So there you go. Field of fractions of a field is, as you should expect, a field. And this completes the proof.